Okay, so maybe I can start with my presentation. As every time, we introduce briefly our organization. The organization is the Society Systems Man and Cybernetics from the IEEE. IEEE means an Institute of Electrical and Electronics Engineers, and System Man and Cybernetics Society is a society with more than 4,500 members. It has three main topics, one related to system science engineering, one related to human machine systems, one related to cybernetics. There are many benefits in being enrolled in System Man and Cybernetic and in IEEE. This is the membership fee, and as you may see, if you are already an IEEE member, you can enroll with a few dollars also in our society. We, as Italian chapter, we are organizing various things. Last year, we received the Most Increased Membership Award. We give every year an Early Career Research Award. This year, we will soon open the possibility of nominating young professor. We are sponsoring various conferences, the conference on technology for defense, on cyber humanities, on enabling technology for infrastructure, on metrology, on human machine systems, on cognitive and computational aspects, and so on. The main conference of System Man and Cybernetics will be in October in Vienna, and we will organize also an System Man and Cybernetic Italian Section Day that will be in Perugia next September, and the workshop that will be in Florence next October. We are organizing also a list of seminars, and as you know, today is Professor Gina Tang, that I am very happy to introduce. She is a professor in the Rowan University in New Jersey, and her research is mainly devoted to cyber-physical social intelligence, and she is working on modeling and control for adaptation and personalization. She has a lot of US patents, over 250 impact publications, and a lot of, she got a lot of awards as listed in the bio. And she is also chair and founding chair of some IEEE technical committee as the one on intelligent solution to human-aware sustainability, and the one on sustainable production automation. Today, she will present a lecture on personalized CPSS for enhanced situation awareness. So, Gina, please share your screen and start your presentation.
Great, thank you. Let's see. Can you see my presentation mode?
Yes, yes.
Okay, great. Thank you, Laura, for the great introduction, and hello, everyone. Good afternoon. It's my great pleasure to be here and as part of a 2025 SMC Italian chapter lecture series. So I'm Gina. I co-direct a center with my colleague called Machine, Artificial Intelligence and Virtual Reality Center, MOVIC. So in my presentation, I would like to share some recent efforts and development with the center. So I'm going to play a little bit of video of this center. MOVIC is a research center dedicated to explore the dynamic fusion of virtual reality, augmented reality, and artificial intelligence to redefine the new boundary of immersive experiences. We truly believe the convergence of those technologies present a lot of potential to transforming the human-machine interaction, present a lot of opportunity across various domains. As you see in the video, we bring a learning into the virtual space, and we're training medical students, and we make those high fidelity virtual reality scenario to give the experience in very safe and controlled setting. And we do similarly across a variety of different population, ranging from K-12 to up to higher educations. We're also working with defense industry. In this video, we show them how we bring those training design to mimic a complex and pressure high-stake environment to really train the next generation gunner to improve their survivability. Of course, we also worry not just about the environment, but more about the cognitive readiness. So we also engage some physiological sensors to understand the fatigue level and stress level, and engage, integrate those information systems to the virtual and augmented reality platform to fully help them to make a decision, not necessarily for the gunner only, but also for the commander to make the decision making at the right time. And we do very similarly, and also working with, so for this video you guys show, that's the augmented reality. We allow people, gunner and commander, to see a variety of the information that become available in real time. And we do similarly working with Federal Aviation Association to help improve pilot safety. And we do a variety of artificial intelligence
mission accomplished.
Project to try to identify the cockpit and the parking space, and as well as we develop a variety of symbology to design a head-up display, head-mount display. So with the technology advancements, we realize the emergency of multidimensional reality, as my title shows, the cyberspace and physical space and social space. Really, the technology, the emergency present a lot of opportunity and as well as challenges. The immersive computational power make everything connected, not limited to time and space, and many abstract and concept and large data sets become available, accessible in a way that's more vivid, dynamic, and interactive. You can imagine if we bring the entire human anatomy into the virtual space, how much we can do to train a medical student and practitioner that's never been possible in the past. And as I mentioned earlier, this emergency, the multi-dimensional reality present a lot of opportunity at the same time and challenges. So one of the big challenges we try to deal with is truly to understand the intersection of human, machine, and the natural world. So we can come up the principle mechanism to really command control the reality. And out of all the challenges, the fundamental one is to address the human factor. A lesson learned from process automation, as I stated in the slides, the human factor, if the human factor are not taken into consideration, even technological state-of-the-art system can be more problematic than beneficial. So in the rest of slides, I'm going to address how we design those cyber-physical social systems to tackle the social dynamic in two of the domains. One, we look at the education system. So talk about learning, and let's look at what is the situation of wellness in learning. And when we talk about learning, we have to mention the two famous philosophers, Jim Paget and Levi Vygotsky. So Dr. Paget think learning stems from individual exploration. So from his view, there's a group of scholars has followed him to actually create what we call constructism and experiential learning. And on the other hand, Dr. Vygotsky thinks the learning is not just individual endeavor. Rather, it's culture and social interactions. And people learn much more by interacting with others and learn from others. So his view actually leads a group of researchers and to have those what we call collaborative learning and social learning. And from our view, we think those two are actually complement each other. And so if we are going to design any tool and platform to support education, we have to come up with a way to present the opportunity for students to do the individual exploration at the same time interacting with their peers. So more importantly is through those learning process, we should come up with the mechanism and principle to really enhance student understanding, their own understanding of the learning. That's from cognitive and metacognitive perspective. The more students understand their own learning, the better they're in the position to regulate and monitor and adapt for success. So with that being said, what we have to is looking at what challenging the education system is facing. If you look at the current classroom, probably hasn't changed much from a decade ago, right? We still teach subject in isolation. It's very difficult, if not impossible, for professors and teachers to really understand individual difficulty of the student in the learning process. Think about, imagine you're standing in the classroom with 30 and 40 students. It's very impossible for me or for any of you to identify the subtle difference of the student to differentiate A from B. And since we can't differentiate, know the difference, it will be difficult to come up the process to provide individual and personalized learning. In the other end, no matter how we don't change the education system, the student learning habit has significantly changed. Many of us not only sit in the classroom to study, there's many virtual and learning classrooms, and we can take the online classes and do the certificate and get the learning. And on top of that, there's many platforms such as Discord, Instagram, and Slack that offer the opportunity for teacher and student to communicate and collaborate together. And these changes actually present a very good opportunity for us to understand students. As I mentioned here, there's many data, much of the data and flow through the platform from one end to the other end. If we would be able to capture those data, we are in better position to understand the subtle difference of a student from A to B. So with that thinking, we actually, at Mavic, we try to design this parallel intelligent education system. We engage students in the physical learning at the same time. We digitize learning. We gamify the learning material and mimic this part of learning in the virtual space. So I'm going to show a couple of examples here. I believe many of you are either in computer engineering, computer electrical engineering, or computer science. There is one core course called Digital Logic Circuit Design. So in Digital Logic Circuit Design, you usually engage students to design the circuitry and download the FPGA. And we come across traffic light on daily basis. Probably and so, few of us would think, oh, the traffic light is a typical digital logic circuit, and it's a sequential circuit. We often in the classroom have students design traffic light controller. And we do similarly, but rather in download to the FPGA, we engage them into the virtual space and present this narrative. Students are facing and witness a traffic incident, then they're called up to redesign the traffic light controller. But what we build upon that is not only present a narrative, we present a lot of learning too in the virtual space to guide them solve the problem. And we're doing similarly, but this example is down to the K-12 level. We actually inspired by a famous fiction book, a children's book called Magic School Bus. If you recall, in that book, the teacher always, took student on fantastic journey to learn the science and close up. And we do similarly in the game. We invite a student to board on the rocket and shrink down and go into your human body to learn and explore cells, organs, and biological system science. And for instance, we even try to teach students about motion and force and using the metaphor of racing car and to mimic how red blood cell transport oxygen and carbon dioxide. And we do similarly for many other mini games as well. So this is a multi-person game. So students will interact with others and chit-chat together to understand some of the situations in the human body. And one thing, we actually confront them with the sickle cell to understand what's really happening to the cell that becomes sick. And you might think about teaching AI is very difficult process to the K-12 student. But if you're looking one of our game, we actually introduced the digest system with student going to your tongue and going through the function of the teeth, saliva, but more importantly, under your tongue, there is a 5 sensor, right? To taste sweetness, salty, and sour. And that's exactly how mimicked machine learning, right? The brain is actually collecting food, and that's your data source. And then depends on different flavor, they doing the classify, the putting the different things about the sweet part and salty part and sour part. And later on, when you have one food, you immediately tell your body, oh, that's a salty food versus a sour food. That's exactly the process of a machine learning, but we're using this real, your body functionality to show students about AI and machine learning. So with all this digitized learning process, we actually, help solve one issue, which is making learning more fun. And more importantly, when we digitize the learning, we present opportunity to lock student behavior inside the learning process. In this case, we would be able to gather the big data to reflect the student behavior. With that big data, we would be able to build a lot of AI-empowered NPCs, what you call agents. So these agents are going to provide a variety of different type of intelligence to help understand the student, at the same time provide individualized guidance. So that's how a project called Personalized Instruction Need a Well Gaming, we call Ping. If you recall, Ping is actually a very old command when the internet was booming, right? That's ping where you are on the network. So that's great analogy about what we designed those recommendation system to ping student where they are in the learning process. So as shown on this slide, where we have the pin system, we actually engage student in the physical learning. At the same time, we mimic the part in the virtual space. In addition to the mimic part of the learning, we also build tutor agent and peer agent. So tutor agent is straightforward. You want to have teacher inside the learning process in the game, right? But this tutor is integrated and powered by AI. So it's integrate multiple good teachers' knowledge together, right? At the same time, the learning is social. So we also building your classmates inside the gaming environment, and those peer agent or interacting with the player together and learning the process, going through the learning process. So the peer can comfort the student, and peer can be, very smarter than you. So they can help you through the learning. Or the peer might have less knowledge than you. So you end up teaching the peer, then reinforce mutual learning. That's also one part of learning strategy called Pache effect, right? Teaching by learning by teaching. So that's typically the structure. We have the game. Instead of having game as shown in the previous video, we also embedded what we call social cognitive theory-based probing. We literally embedded a mechanism to trigger you and get you response about your understanding, your perception of problem solving. So those data coming back and fitting into our machine learning module so we can understand and draw the profile of student. So this is showcase what we do the probing. And particularly, we can have those probing inside the game and to help us understand the perception of the student in terms of task variables. And so similarly, as you see, we can insert quizzes. We can insert various mini games that's also target driven. So it depends on how you respond to those prompts, and we gather the data about your specific needs and limitation. So with those probing mechanism inside a game, we can gather the data. That's actually individual players' response to those triggers, to those in-game or external stimulus, and we call those as features. So we collect those feature and together and put in a vector. That's the feature vector that corresponds to individual student learning behavior. So with this feature vector, we actually can categorize individual student, okay? Whether they're a type A student, type B student, or type C student, how much they understand the fundamental knowledge to carry on that to solve the problem, all captured in this feature vectors. At the same time, we use the formal model. Why do we use the formal? You can imagine the game or learning process. That's a dynamic evolution system, right? The player was positioned in the game with continued evolution and the change with their knowledge, their emotion, everything changed along the learning process that actually evolved the game itself at the same time about the student knowledge and understanding. So with that being said, you actually can engage any formal model to actually modeling that learning process and that evolution process. Through that modeling process, you also can see how players are going through this learning process. So with that being said, in our process, development, we use patronets, but that's not limit to patronets. You can using supervised automata, state machine, and any other formal model you are comfortable with. But the idea here is you want modeled every stages of the learning. And of course, be able to associate the student characteristic into the learning process. So as you will see, we modeled every stage of the measurement. Those measurement is going to help us update the student characteristic, which is the feature vector. As the player going through the learning process, the feature vector are changing over time. And of course, with this model, you will come across several decision-making stage to decide which learning paths that best fit this player, right? And with that being, the model itself probably cannot make a decision. But in this case, we actually think about what else it can help us model to make a decision. And at the very beginning, the agent doesn't know anything, okay? As they're observing and interacting with the student inside the gaming process, they start to know people. And with that being said, we realize that's typically reinforcement learning. So from that point, we had a model, then we built reinforcement learning on top of the model. And to help us to identify how students grow through the learning process and provide some action suggestion to guide the student and pick the best learning paths that suit for the student. And of course, with the time limit, I'm not going to go through the detail, but I'm showing case the development process of with the reinforcement learning and our formal model. If you're interested, I does present some of the reference in the slides. You can refer to that. So when we started building the reinforcement learning, and we noticed that some dilemma we're running into. And apparently, the more data we have, the better we are to understand student. But as we have more data, the state become exposed, right? And so the state space become huge, and it make it difficult for reinforcement learning to converge. So that's after we building the model and the reinforcement learning, we come across several iteration and variations. So one thing we did is building hierarchical reinforcement learning. So instead of have one agent, reinforcement learning agent, we have multiple agents. And we have upper level agent to decide which fundamental knowledge you're lacking at the moment. Then we're going to lower level to really, drill down to that particular knowledge you lack of, and then getting study learning material to build up your foundation before you move on solving the problem. So this is one of the example. You can see that when the play come in here, and it will measure their understanding and using those probing and responses. At the same time, the student data are being updated, and depends on what your knowledge understanding at that moment. The reinforcement learning may suggest you go into a specific learning block to enhance that particular knowledge. And once that particular knowledge being enhanced, you come back and to see whether there's any other knowledge you need catch up before you finally solving the problem. So as we show that when we building the hierarchical reinforcement learning, we have upper level agent and we have low level agent. Each low level agent are in charge of one of knowledge. So of course the knowledge might be different, but ultimately those knowledge are together to try to solving the same problem. So with that thinking, we thought maybe the low level agent have some knowledge that can be shared rather than they doing this exploration themselves. So with that being said, we move on from hierarchical reinforcement learning to come up some transfer learning mechanism to design this weighted experience sharing. We allow agents to share experience at the lower level to enhance their convergency speed. After doing that, and we also notice that if we share experience with all agents, it takes time. But it turned out we don't need to share all of them. We should share with the closest agent, with the similarity high agent. So doing so, we actually move forward and to modify the experience sharing mechanism with a selected group. So how do I decide the similarity of agent? Since we're using deep reinforcement learning, so deep reinforcement learning using the deeper neural network. So we actually adapt the mechanism to decide similarity of neural network to decide the similarity of low-level agents. So this is some of the experiment test results. As you show here, if the agents are converging or perform better if with experience sharing. And so the blue one is no experience sharing, right? And of course, the best one, as you see that the way that the experience sharing with the tutor agent with the selected group is the gray one. The gray one was not performed the best compared to experience sharing with all agents. But what we particular interest is when the reinforcement learning are not having enough data to make a decision. So it's a very beginning stage. You will see that the beginning stage, the gray line perform much faster and better than the orange line. So although at the end, the gray and orange are converging to a certain point, so we think that trade-off is necessary and worth exploring. So besides the tutor agent, we're also building the learning companion, which is the peer agent. Try to provide more encouraging emotional support to the student. So the learning companion we try to build is actually leverage large language model to actually promote several different skills that tutor agent may not be able to promote, and particularly those team building skill sets. So what do we try to do is we engage the large language model, and if we don't, before we have large language model, we have the fixed dialogue. So with the large language model, our conversation become more dynamic, and also to prevent large language model to hallucinate it. And we wrote those prime templates with RAG, retrieve augmented generation. So as you see that we particularly set different filtering mechanism to make sure our responses are fit to this context as well as fit to the age level and to that particular educational topic. And after prompt tuning, we can do fine tuning. So if without fine tuning, you will find some of the comments conversation are easily stopped at certain point. It's not very helpful, particularly to the student, low performing student. But with the fine tuning, the large language model can strive to ask a question in a variety of different aspects. One thing I want to share with you is actually we currently working on just try to convert large language model to large action model in the game. So rather than just having conversation, we allow the game system to sense the conversation and to be able to change the scenario and change the action in the game. So I'm going to show you one of the demo. As you see, the cap is a large language model agent, and the player is trying to communicate with him, right? So, and rather than just have a conversation, pay attention to his smile, right? His facial expression. So he can change the facial expression to be smiling when people are greeting him. And the player next was asking the cap to say, how about you follow me? And Cap was responding, say, sure, I can come with you. So look at, after that, so the player is walking around and Cap is following him. So apparently Cap is able to decipher the conversation and make actions. We are actually running the local, large language model rather than using the API. So you see the CAP was a little bit responding slowly. And of course, sometimes he makes mistakes as well. So the last conversation the play was getting to tell the CAP is ask him to find a particular red blood cell. So CAP is looking through and try to think of, well, the designate red blood cell. And the red blood cell that's designed is actually on the top on the hill. So it took CAP a little bit time to, I think, figure out the way to go up and to meet the red blood cell on the top. That's the one he tried to meet. That's beyond the large action model. And another thing we try to do right now is we have designed those tutor agent, we have designed a PO agent, and we found it very useful to the learning, and which I will show you some of the pilot data. But we realize how to reuse this intellectual property, how to make our design of tutor agent and peer agent as a plug and play tool. So everybody else design those learning environment, they can, if they want to engage those agent, they can use our design. So with that, along with that thinking, what we try to do right now is come up some symbolic AI, neuro-symbolic AI. So, and typically for this case, we try to use ontology to come up some symbolic reasoning to integrate peer and tutor agent together. So with the ontology, they can quite good to classify, categorize all the concepts that being taught to different audience. Then we can design variety of reinforcement learning that target to individual concept. When we try to plug and play our tutor agent and peer agent, one thing we run into is different learning platform may output different data about learner. So how do I take the variation of the student data come from the learning environment and mapping to more unified outcome that will be sent to our reinforcement learning agent. So another thing ontology try to do is define the symbolic reasoning and do the mapping from the outputs coming from the learning environment and to the inputs that goes into the reinforcement learning agent. And of course, this kind of type of work are still in the preliminary stage, and we have some conference paper published. We continue to explore what, reasoning will guide those mapping quicker. And this is some of the pilot data I want to show you. And when we're using the tutor agent, and apparently with the guidance, and the student show better performance in terms completing the task, the problem solving task quicker than the people without AI guidance. In terms the engagement with the game and working with the peer agent, we find out student interact with the learning process with the peer agent, they have a higher retention rate, and it shows high engagement through the game. So those preliminary data does provide a lot of motivation for us to continue in that directions. We're using very similar idea to go into aviation safety. So let's take a look at what's the situation of wellness in aviation. So to improve the pilot safety, we want a pilot to be aware about the environment, right? Aircraft state, location, flight condition, configuration, and so on and so forth. Also about external factors such as the terrain, obstructions, weather. But more than environmental wellness, we also want pilot to be aware of their cognitive load. If they are stressed and fatigued, maybe they're not in the better position to make a decision. Out of all the literature, we see that about 88% aviation accidents are caused by pilot-limited situational awareness. Out of that, 76% are due to the pilot field perception, which means pilot has wrong perception of their situation, whether about environment, whether about their personal cognitive workload. So in the past, when we're doing aviation testing, we all come to the hangar, right? Doing those physical testing. The physical testing sites still exist, but the testing are now transitioning to virtual. So as you see on the left-hand side, this is a retired helicopter. And we're using the retired helicopter and building a variety of different virtual and augmented reality tools inside the cockpit to provide head-up display or head-down displays. At the same time, we are very interesting about the cognitive load. So we engage some smart watch to measure the pilot physiological data. All together, we integrate together, try to understand what information can be displayed and should be displayed at what time to enhance pilot situational awareness. So those are the research, including we design symbology, we conduct computational experience for variety setting to improve the visual dominance issues. And of course, research are guided by the problem we're facing. While we're doing this, we're coming into a very interesting problem, particularly when we gather those biometric analysis. We were testing here on the left-hand side, doing the real testing with the real retired pilot, Anna in the picture here. And we do engage a set of sensor with the camera, with the pupil dilation measurement. But unfortunately, she's moving her head very frequently. So this kind sensor actually always, she's out of field of view of camera most of the time. So the camera has to do recalibration again, which is very impractical. And of course, at the end, we got nonsense data. It doesn't work. So that actually motivated coming to the next research agenda is say we find out many sensors that show high accuracy, including EEG, gaze tracking, pupil dilation. They are very good, but they are very impractical, due to the high cost and noise sensitive to noise and the effort to do the setup. So the question keep coming back to us is, we know those sensors works. They work very well in the controlled environment. Can we transfer that knowledge gained in the controlled environment and into the real world scenario? So we keep asking these questions, and we actually did a little bit of exploration. So we tried, and we actually designed this multimodality, multi-stage framework for fatigue cognitive load detection. The idea is you have a set of the sensors that are practical to use. For instance, the heart rate, the skin detection, PPG, and so on and so forth. They're all good in the practical setting, but you don't have EEG and gaze tracking and pupil dilation. But you could do that in the controlled environment. So you could thinking the practical sensor has missing modality somewhere else. So when you're doing the control data, when the control experiment was conducted and gathered the data, and to you are thinking, how can we fuse them together? Okay, so from that thinking, we actually come up some strategy to impute those different modality and eventually fuse them together and to enhance the fatigue detections. So typically you can think about whenever you have the control data available, you can start to bring that new perspective into your detector design. And of course, because the sensor setup are different, you have to come up some cross-staging and prevent the data trend shifting issues using some of the methods. But overall, you hope the detector accuracy are increasing. So we actually did some preliminary testing with 3 public available data set. The fatigue set is the one we gather, and we put, using our own sensor to gather the data. The BPFD and MEFA, they are public available in the literature. So we use those, public available data set, they each with some overlapping and unique signals. And from this testing, and of course we use existing method to do the detection, we find out the more data when you combine and the detecting, we can progressively improve the detection accuracy. So of course, this is the preliminary study that actually indicate this direction is great. From that point on, we are working on to have more sophisticated imputation method and engage the graphic neural network to try to model the relationship between individual modality. So with that said, I just want to summarize my talk today. We believe the cyber-physical social intelligence is the future, and there's 2 core components are very important. In the cyber-physical social system, there are a bunch of sensors. They are the eyes to sense, to measure, and then transmit those data to us. And at the same time, we would be able to continue monitoring and track those data. Once we have the data, then we're building the model using artificial intelligence and machine learning, and they become the brain of the cyber-physical system, so we can make a decision to adjust, adapt environment, task, and provide different assistance and guidance. So in the future, as I mentioned, the big challenge we're facing, no matter what system we're design, is the human and social dynamics that make our system more uncertain and diversified and complicated. So they're looking for more of us as a scholar to devote our effort to using those AI and knowledge automation to bring those uncertainty, diversity, complexity, and merge into agility, focus, and convergence, and to achieve the sustainable future for a better future and better world. So the last sentence and quote I would like to say is, I call for many efforts from us and from you to join us. I actually has working with many of you colleagues, including Magrazzi, to have a TC on intelligence system for human wealth sustainability. And that TC actually organized annual conference. Many of the colleagues in the audience are joining us to help us organize this conference called Cyber Physical Social Intelligence. This is the 5th year. We had many years in the past, and this year we're in Macau. And if you're interested, you can scan the barcode, and that gets you into the conference site to help if you're interested in contributing and organize future conference, please join us. We need more efforts and more talent. And at the same time, the group of people, us, and start design, launch a new journal called Journal of Cyber-Physical Social Intelligence. We have open issues coming up soon. And if you're interested in contributing, and please scan the barcode and to join us to make this world better and better and more sustainable. And final notes, as I mentioned that, I have this intelligent system to human wealth sustainability, and many of you are part of that. So our TC continue growing, and we're looking for more of you to join us. If interesting, contact us. We work together for a better future. Thank you. That's all I want to talk today. And that opens to the floor for any question you might have.
Thank you. Thank you very much. So please, your comments or questions, curiosity. Giuseppe?
Yeah, I have some questions. So Gina, thank you very much for your talk. As you know, I'm also working in situation awareness, and this year I'm also leading a project on a similar topic. So we are trying to apply situation awareness to e-learning, and in particular to the micro-learning approach. So micro-learning is when you have an e-learning course, but you have very short modules, very short videos. So and we are also using something like gamification, for instance, like a Duolingo or this kind of app, because we believe that especially the younger generation are very prone to use, I don't know, for instance, YouTube or other kind of sources for learning, because they want something very, very short, something very direct for their problems and so on. So we are trying to use this approach in order to foster a more, let's say, well-designed course using the situation awareness approach. But I want to know your opinion regarding this. I believe that what you showed about the virtual reality is very, very interesting. But in my experience, it requires a lot of time and effort to create this kind of application. And so I don't know if it is feasible to realize, for instance, a complete course using this kind of approach. So I just want to know your experience regarding the effort to create this, and if you think that the new technologies like the generative AI could help in this process.
That's a good point. You mentioned that you want to keep the learning short because the attention span is short for the kids. That's true. Even my game, we try to keep like 30 minutes as a match. Mm-hmm. And because the attention span are very short. But students like it. The challenge for us, as you see, VR is great, right? And when students look at the VR and gaming, they'll say, wow, at the very beginning. But how to engage all the time is a challenge we're facing. So it's always a balance between the learning and fun. Because as you see, we do have quizzes in the game. If we have quiz all the time, sooner or later, students realize, oh, this is my regular class. I no longer interest. So we are trying to debating how to maintain the balance. That's a challenge we'll continue resolving. The second time about effort, the second question you said effort. Yes, design 3D, immersive, this one, I show some of the development they actually publish to the phone app. So they don't have immersive feeling, but they still feel fun and convenient to access. But for those development does involve a lot of effort, the human effort to design and developer. Particularly a lot of 3D model take time to design But to answer your question, yes, you're on the right track. The AI, the generated AI, has made our life much easier. Before, we have to start the storytelling. Right now, we can have general idea, then communicate with ChatGPT. They gave me a very beautiful storytelling idea, transcript. And even creating models. We have a set of artist visualization team. They doing all the modeling design for the project. They are starting shifting a prototyping a pipeline to using generative AI. It's going to save tons of their time. But still, I think a human in the loop of design is necessary. A lot of generative AI outcome are not looking real and good in the contextual level. So we still need, artist of, illustrator to help us improve the model. To answer your question, yes, that's the dilemma. But I think for my project, because they are more research exploration, and if you want production to support the entire education, and one thing you can think about, rather than doing the 3D, you doing 2D, the web design. So you lose the immersive, but you still keep the fun part. That's easy turnout. Another thing is just waiting for the generative AI to continue booming, and they will definitely help. We already see the timeline turn out to be shorter, like 40% now. So yes, it's going to change down the line, but not yet there yet.
Thank you.
So if you're doing similarly, we should continue talking and collaborate along that line.
Yes, and regarding this, now we are in the evaluation phase. So my second question, my other curiosity is, I think that you evaluate both the, let's say, the outcome, so the results in terms of learning, but also the engagement. My curiosity is if you also test and try to measure the level of situation awareness of the students or not.
We have not. That's a good question. We never test, we never ask question. We do have attitude survey, but that's only done at the end of the pilot. But if you want to measure through the process, that survey should be intermediate in the learning process, but we have not done yet. But that's a good question. Definitely, I will include it in the next round. Yes.
Okay. I was also curious about the impact on students. So I know that you are measuring, but my question is, do you compare students using this method with the students that were using a classical method, like classical class? And what is the comparison? So do they learn more?
I did show, yes, we did compare in my slides, and there's one part that's I can continue showing that. So you will see this slides. This part is the comparison, and we do have a comparison. This is the one. We have Gridlock is the game, and we designed the game first, which has no AI, and then we engage with the AI tutor agent and peer agent. So we show the difference. The baseline is without AI, and the proposed case is with the AI. So to answer your question, yes, we did compare the student without anything. So this is the test data to show student would play a game without AI. But before, when we started design Greylock first, we do have comparison between people using game versus people using traditional method, which is doing FPGA design. So we find a very similar trend to answer your question. So the student actually spend less time using my virtual reality game to complete the traffic light design versus the traditional one, they're doing their own and writing the code and download to the FPGA. So, and for this engagement, because we didn't compare for the peer agent, so we only ask a student play the game with the peer agent and the student play the game without the peer agent. And this is coming from the responses inside the game. So we have some questionnaire answer. They have the answer at the end. We have some of, let's say we have some of the side playable mini game on the side. So student can choose to play or choose not play, is optional. But usually when they talk to peer agent in the game, peer agent always encourage them to play because play more mini game will enhance their knowledge. We turned out find out student does take the peer agent recommendation and play those optional mini game inside the game. The one with no peer agent, since there's no conversation whatsoever, so the students just do as they like. They may miss those mini game opportunity at all. We didn't compare, for this case, we didn't compare with the student that never played the game. But we did have a survey at the end of this pilot, just happened last month in April, and the student all recommended, give very good thumbs up, and they say, oh, I would like to recommend this one to my friends because I thought it very fun and I learned a lot, and I'm sure they will learn a lot as well. So based on the comments, I would think they're still better than traditional method.
Okay, there is a question from the audience. Zia Rehman, please go on.
Hello, my sound is audible. Ziaur Rahman, a PhD student at University of Salerno. I have one question. Recently, I completed one project on situation awareness in mental health care domain. My question is, are you try this system because some students have some mental health issues like ADHD, attention deficient hyperactivity disorder, like they will be played 3-second game and 4-second game. And have you tried this some mental health patient also?
Yes, the very beginning of the video, if you replay my recording, there's one video and showing we're helping the autism kids to
Okay.
dealing with. So that video was showcase not helping the autism kids, but we're helping the family, the parents, to deal with autism kids. And before that, we do have a video game to help to working directly with autism kids to help them improve their social skills. So we engage them in like a Christmas shopping, for instance. They have to go to different shop and purchase a gift for their parents and relatives. So they're running into, they have to communicate with, personnel in the shop, and even some people waiting in the line. So we kind of create those scenario to guide the autism kids to facing the challenge in social interactions. Yes, to answer your question, yes, we do have those kind of type of design.
Thank you. Thank you. If there are no
Gina,
other...
short curiosity
Gina, go on.
at the end, just to understand, since the system is really relying on AI, and there is a lot of discussion on trustworthiness of AI, are you also guessing about aspects or requirements like explainability of AI or security? Are you also discussing this kind of requirements in your systems or advancing it in the future?
Yeah, definitely. That's a good point. And we have another team and particularly working on trustworthy and explainable AI. So this is this particularly, we have a game working with the K-12 student with minors. So we do engage the school, higher administration and teachers, and including the parents in our focus group. as an advisory board. They're looking at those development. Another end is from the technology point. We engage with RAG. We have a supervised agent design on top of a large language model, which is another large language model on top of a large language model. So we have those safety procedures, but at the end, whether it's safe or not, it's still a question mark. It's a goal we try to achieve. Let's put it this way.
Thank you.
Thanks.
Thank you very much to everybody. And if there are no other questions, we thank again Gina to be with us today. It was very interesting. And so I think we can close our session today now. Thank you. Bye-bye. Bye.
Thank you. Thank you, everyone, for your attention. Talk to you soon. Bye-bye.
Yes.
Bye-bye.
Bye.